Here are some applications of sequences and series. These three focus on geometric sequences. So this one is dealing with population, and the question gives me a whole lot of values for population. So I'm going to start by putting those into a table. So in 1870, the population was 3.5 million. In 1910, my population was 7 million. In 1950, I was at 14, and then 1990, I was at 28 million. So what I want to know is if this pattern continues. So I would have, 2030 and then 2070. What is my population value here? So hopefully you can see that I'm multiplying by 2 in each. This is going to tell me that I'm dealing with a geometric sequence, which I know my general term is in this form. And then I've got my R value and my N. Now, when I'm dealing with a question like population, this is really at the beginning of the year here. So we usually call this value U0, and then U1, U2, U3, U4, and U5, because we're looking at the end of the time period. So when I set up the equation for my general term, I've got UN is really going to be equal to, I'm just going to modify this, U0, which is actually the first term or my initial population starting at the beginning of that first year. Then my R value, which is 2, and then N. So now what this is going to allow me to do is solve for U5. Here, just using my calculator, I've got a 5 there. So then I've got 32 times 3.5, which tells me that the population will be 112 million in 2070. The next one we're going to look at is a population one as well. And here we've got the town of Springfield has a population that is growing at a rate of 1.5% per year. So this is going to tell me what my R value is. And my R value is actually going to be 1 plus 1.5, okay? Or really 100 plus 1.5. Because every time I go through a new year, I'm going to have my original 100% from the year before, plus an additional 1.5%. When I change that into a decimal, I'm going to get 1.015 as my R value. Initially, the population of Springfield was 8,400, so that's like my U0 or my initial term. Okay? And then I'm going to write an equation to model the population of Springfield. So here I would have my population, my initial term, my R value, and then my N. And in this case, I'm going to use T because that's what it asked me to do in the question. Okay. And I should have noticed, because it's growing at a rate, this is going to tell me that it's a geometric sequence as well. So now I'm going to use that equation to determine the population of the town after 4 years. So 8,400, 4. I'm going to use my calculator for that one. 8,400 times 1.015 to the exponent 4 is going to give me a pretty big number. So 8,915 approximately people. Okay. The last part is asking you, so this is B, A. The last part's going to ask you to solve for when the left side is equal to 15,000. This is sort of going back to our probability unit, okay, where I'm being asked to solve for T. The first thing I'm going to do is divide both sides by 8,400, which is going to give me 1.786 1.015 to the t. Now I'm going to take the log of both sides, like this, which is going to allow me to bring that exponent down in front. So when I divide both sides, so log of my 1.78 number divided by the log of 1.015, that's going to give me approximately 38.9 years. So we can round that to approximately 39 years it took the population to get to 15,000. Okay. Last one we're going to do is half-life, which is another application of a geometric sequence from nuclear chemistry. The time it takes for a sample, half of a sample of a radioactive isotope to decay is called the half-life. Iodine-131 has a half-life of 8 days. Write an equation to determine the amount of iodine-131 remaining in a sample after n half-lives. So let's start. So because I've got a rate here, so I'm decaying by half every 8 days, this one's also geometric. Okay. So in order to write our general equation, we're going to start off with our general term. And again, I'm going to use U naught here to represent our initial value. So on the left, that's going to be my amount of iodine, so I'm going to call that A. Here, this is going to be my initial amount of iodine, or A naught. My R value is going to be 1/2, because that's how much it decays by every half-life. Okay? And then N, this is just going to be the number of half-lives that have occurred. So if I were to fill in my information here, my initial amount is, that would be it for A. Then for B, I'm actually going to put some values into my equation. So my initial value, that 200 milligrams, and then after 32 days, so 32 divided by 8 would give me 4 half-lives. So that's going to be my exponent, which is going to allow me to calculate my value here, which is going to give me 12.5. So that means that I would have 12.5 milligrams of iodine-131 left after 32 days.